share my screen. Actually, first I have to find my talk.
Okay, so we are glad to have Larry Blume with us. Or, oh, he's here still, yes.
I'm still here.
So Larry is from, as you could understand, from the gorgeous town of Ithaca. That is, he's a Cornelian. This is the adjective Cornelian.
Cornelian, yes.
Cornelian, yes. And he's going to talk about, as you can see, approaches to pro-social behavior. Among others are altruism. I'm reading now a book by, what's his name, Andrew Dicker. It's called The Altruists. But it's really about the fight between millennials and boomers. And mid-book, I still don't know who are the altruists there, so I cannot contribute anything to the talk. So it touches upon everything: psychology, game theory, biology, of course. So please, Larry, go ahead.
Okay. Thank you for having me. It's my intention to talk for, I hope, around 40 or 45 minutes, and then we'll have time for discussion. And I had originally prepared an hour-long talk, and then learned that I had to cut it down a bit. If I had more time, I would have spent, time talking. Talks on altruism typically begin with a discussion of the English philosophers, with Hobbes and Hume, and their very differing views of society. Hobbes, wrote about absent any controls, the life of humankind would be solitary, poor, nasty, brutish, and short, a war of all against all. And so his solution to this is government and social contract and a sovereign monarch. And Hume takes a different view, which is that informal social relations solve the problems that Hobbes raised. And there's I would say, certainly over the last 50 years, or certainly 50 years, I guess, there has been a literature coming out of rational choice social science, which tries to understand how Hume's vision, how Hume's vision might work. So I'm going to talk about some of that work. And I didn't know much about who's in the audience. So this talk is in an attempt to be broad, is at a pretty elementary level, but in questions or conversation after the talk, we can certainly go into more complicated models that display a bit richer behavior. Okay, so I want to talk about three things. I want to talk about reciprocal altruism. I want to talk about the importance of social structure for delivering both pro and antisocial behavior. And finally, I want to talk about, very briefly, I suppose, about the evolution of preferences. Okay. So here are three different game theoretic models, three different kinds of social situations that I'm going to talk about in this presentation. And I think there's little to say about the prisoner's dilemma. Probably all of you have seen the prisoner's dilemma before. And the object idea is that even though this is a social situation of some kind, there's not really any interaction between self-interested individuals here, because it's obvious that there's one thing to do. And so for the non-game theorists here, let me say this is we have two individuals interacting, someone who chooses a row and someone who chooses a column in the table. The row and column choices define a box. The number on the left is the payoff to the row. The number on the right is the payoff to the column. and bigger numbers are better for individuals. These are either utility numbers or these are material benefits, depending on the context, and more is better. And so it's obvious here that no matter what the column player chooses, the row player wants to choose D, and similarly for the column player. Now, so there's not much you can do about this, but questions about the prisoner's dilemma, and there's Bob Axelrod's book on this is famous, The Evolution of Cooperation. The idea is to change the nature of the way in which people interact in some way, a group of individuals interact in some way, even while having this simple two-person interaction here, and then seeing how the context of the game actually changes the opportunities for what can be achieved. A second kind of social situation is that of coordination games, where here the object is clearly to there are the story of the game simply is that people would rather coordinate than not. And it's better to coordinate on one thing than it is to coordinate on the other thing. It's pretty obvious, what we would like to happen, but the question is what kinds of social arrangements. There are two natural settling points or equilibria in this game, where everybody coordinates and gets two, or everybody coordinates and gets one. The question is, and they both seem to be stable behaviors in the sense of Nash. And so the question is there reason to favor one of these over the other? Are there forces when we embed these things in this kind of interaction in some social context that will favor the 2-2 outcome rather than the 1-1 outcome? And the last game is a game that's often used to discuss fairness, and this is a very simplified version of it. And we're going to look at a more complex version at the end of the talk. There's a unit of, or two units of resource to split, and a first chooser chooses a split of the resource, either a fair split, one apiece, or he exploits the situation and takes all for himself. And then or maybe what I should have said was, instead of all, he takes all minus just a little bit. And then the second player then has to choose whether to yield to this very unfair division or to resist it. If the second player yields, then the first user does get everything, or everything minus a little bit. Think of that zero not as zero, but as like 1/100th or something like that. And if second player resists, puts up a fight, then they both get nothing. Okay, so we'll talk about if material payoffs alone matter, then accepting the split is in fact equilibrium behavior. It's stable behavior in this game, but in experiments, typically with university students, but also with others, individuals in the role of player two tend to punish people that are unfair by saying, I don't want to do this at all, and they take a material hit in order to punish the proposer. And then on the other hand, individuals in the role of player one tend not to try and be too much of a pig. I think in many of the experiments I've read, the mean settles around, they keep around 60% and then offer up 40%. But I'm going to use this game to talk about the evolution of preferences at the end of the talk. All right, so I want to begin by talking about altruism and how in a game like the prisoner's dilemma, cooperative behavior might emerge. So I want to begin by talking about the work of the biologist William Hamilton, who is known, among other things, for the idea of kin selection. And I've written what he has to say here. The social behavior of a species evolves in such a way that the individual will seem to value his neighbor's fitness against his own according to coefficients of relationship. So, evolution selects on phenotypes or acts on phenotypes, but it selects for genes. And, we share half of our genes with our siblings, a quarter of our genes with our first cousins, et cetera, so that a given gene frequency might in fact increase in the population more if we favor individuals close enough to us at some cost to ourselves. So maybe there's an action that I could take that would make me 50% less productive in terms of offspring, but it would, for example, maybe triple the rate at which my sister would produce offspring. And if so, then my gene population will, that will lead to a higher frequency of my genes in the next generation. And Hamilton summarizes this in Hamilton's rule, which says that the degree of relatedness times the benefit to the recipient in terms of offspring equivalence, whatever that might be, has to be, if that is greater than the cost in terms of offspring equivalence, then we will altruistic behavior can be selected for. And we could carry this forward into the social regime by talking about individuals who have pro-social preference. Who am I connected to? These don't necessarily have to be in the social framework. This doesn't necessarily have to be genes, but it's just the degree to which I, internalize in my own preferences benefits to others. But the issue here is that the spread of altruism, if we were relying only on that kind of mechanism, is really very small. Only people to whom I'm related in some way. So there is a challenge. How can we get altruistic behavior in between unrelated individuals? And the biologist Robert Trivers came up with an idea in which he published in 1971. And he thought about the following scenario. He said, suppose that someone is swimming and they start to drown, and there's a rescuer out there who could likely save this individual at only a small chance of drowning in himself in attempting a rescue. And he points out that, well, if this is a one-time event, why would a selfish individual bear that small risk? Right. So the drowner, we wouldn't go and save the person, and the drowner would just drown, but or the swimmer would just drown. But he said, suppose that there is then a good chance that the next time you're swimming, you might begin to drown, and then this person will jump in the water to save you. If there is an opportunity for reciprocity, he argued, then it becomes suddenly a smart thing to do, to jump in and to save the swimmer. And so that's his idea. That's the idea of reciprocal altruism, that it will pay a selfish individual to act altruistically towards another person if at some point in the future that other person will then have the opportunity to act altruistically, back to the first person. Now there's an incentive problem here, because this is only an implicit agreement. Why should the swimmer who's saved today, why should he save the rescuer tomorrow? So to begin with, we have to make sure that they're going to interact tomorrow. There has to be a next day. But then how should the rescuer know that why should the rescuer think that the swimmer is going to save him tomorrow if the swimmer, who tomorrow could be the rescuer, thinks that tomorrow is the last day, right? So in some sense, we need this to go on and on and on. We need really a lot of repeated interaction in order to make this work. And so I want to move this to this discussion to the prisoner's dilemma, to talk about how we can see altruism in the prisoner's dilemma, in prisoner's dilemma situations, and how it can emerge. So this is pretty simple. That agreements can be self-enforcing if there's always a chance for further interaction. To see why, let's suppose that um, uh, each individual announces publicly, I will cooperate with you today. The C stands for cooperation. And I will cooperate with you tomorrow if and only if you cooperate with me today. And we're only going to have 2 periods, but this is a 2 interactions. But these agreements are binding. Once you say this, you have to keep the agreement. If these agreements are binding, let's assume for the moment that the column chooser agrees to the agreements. Then what should the row chooser do? Well, if the row chooser enters into the agreement, he's going to get 5 units of resource or utility each period for a total of 10. Whereas if he violates the agreement, if he doesn't play along and he defects the first period, he gets 6, but then in the second period, he gets 1. So clearly there's an incentive here to keep the agreement, okay? But now imagine what happens if the agreements are not binding. If the agreements are not binding, then in the first period, the role player should think, well, he says that the column player is going to keep the agreement in the second period, but the column player really has no reason to do that. And if the column player is going to quit in the second period, then I am not going to get 5 in the second period. I'm only going to get 1 in the second period, and therefore I should quit the agreement today and get 6 today rather than 5. And so this is the fundamental incentive problem. Let's see how we can make the situation a bit richer. Let's suppose that if there is one round of interaction, the probability of playing another round is there's some positive probability of playing another round. We have, I'll call this a continuation probability. The continuation probability is some number P, which is greater than 0. If we've gone 100 rounds, there's still a probability P of having playing another round. I've written on the slide here the probability that the game will end at the kth stage. And in fact, it's not hard to show that the game will not go on forever, but it will end after some finite number of periods for sure. And the expected number of periods that will be played is 1 divided by the probability P. So in this situation, let's imagine that we have the same kind of non-enforceable agreement, the same non-enforceable kind of strategy. How's it going to work? So in order to do that, we have to compute some expected payoffs. So let's start with an easy one. Let's look at the return to cooperating all the time. Okay. On the assumption that the column player is going to cooperate all the time, what is the row player's payoff going to be? He's going to get 5 today, and with probability 1 minus P, the game ends and he gets 0, so 5 would be the total. And with probability P, the game is going to go on another period, and now we're back in the same situation. And this leads to the recursive equation that the return to always cooperating is equal to 5 plus the probability P times the expected return to cooperating always. And we can solve that recursive equation to see that the expected return to playing this game, knowing that at some point it's going to end, is 5 divided by 1 minus the continuation probability. Similar argument says that the probability, the expected return to defection is equal to 1 over 1 minus the probability, the continuation probability. people who talk about this stuff often talk about this in the context of repeated games where the game just goes on forever and P is a discount factor rather than a continuation probability. But I don't think things go on forever. I think this is a better story. And so that's the one that I've chosen to tell today. So how does cooperation emerge? So here is a strategy for playing this possibly repeated game called, it has a name, it's called the Grim Trigger strategy. And it says, and so here's a kind of a cooperative agreement. I will begin by cooperating, and I will continue to cooperate so long as you do. But if you ever defect, then I am going to play non-cooperatively henceforth and forevermore, so long as the game goes on. Okay. And a couple things so let's analyze this this statement. So the first thing to say about it is that if an individual defects today, then he's going to face defection forever, as long as the game goes on. And so there's no point to cooperating ever in the future. So once you defect, you should continue to defect forevermore. And your payoff from that point on should, turn out, the expected payoff from that point on is 1 over 1 minus P. Furthermore, this is a situation that repeats itself, right? So if you play the game and cooperate, then in the next period, you're in exactly the same situation you were today. And in the third round, if there is a third round, you're in the same situation as you were in the second round, same situation you were in the first round. Consequently, if it pays to defect in the third round, it also pays to defect in the first round. Okay, so we only need to ask the question to understand whether this is stable or not. We only need to ask the question, does anyone want to quit the agreement right away? Okay. And finally, third observation is that if both stick to the agreement, then the outcome will be that everybody cooperates forever, and the return will be, expected return is 5 divided by 1 minus the continuation probability. And oh, my notes just disappeared. Okay. So is it better to keep the agreement or not? Okay, and the return to keeping the agreement is, as I said, 5 divided by 1 minus, if assuming that the other person is going to keep the agreement. The return to if the column player is going to keep the agreement, the return to the row player is keeping the agreement is 5 divided by 1 minus P. The return to breaking the agreement is 6 divided by 1 minus P. I'm sorry, 6 plus P divided by 1 minus P. And you can see that it's better for the row player to keep the agreement if the continuation probability is greater than 1/5. And so what does that tell us? It tells us that in this randomly repeated game, this so-called Grim Trigger strategy is a Nash equilibrium. And there are other strategies as well that will also achieve other strategies that will be equilibrium strategies that will achieve cooperation forever. But it's also true that defecting at the outset, right? I'm just getting 1 forever. That's also an equilibrium. And there are a variety of other equilibria with other payoffs as well. So, for instance, if P is greater than 1/5, it's also possible to support play where people take turns cooperating and defecting alternately, so that you get 6 and then 1 and 6 and then 1. And again, that can be supported with this threshold of, if you screw up, I'm going to punish you forever. So there are many equilibria here. And this is a limit, I think, one limit on how satisfying these reciprocal altruism stories actually are. So I want to enrich this story now a little bit. I want to imagine now that we have a population of players, a large population of players. I guess another point I should have made just a second ago is that looking at two people interacting by themselves forever and ever is not a terribly interesting thing to do. it's more interesting to see what happens in a population of people, and to see if what kind of lift, what kind of reach does reciprocal altruism, this kind of reciprocal altruism have, or this kind of justification for reciprocal altruism, how rich is that? And so now we're going to consider a population with some large number of individuals, and that every time the game is played, we're going to match people up randomly with other people in the population to have this two-person interaction. And when they have this interaction, people, you're going to look, I'm going to be matched with Doobie. I'm going to say, Doobie, I've played with you before. I know what's going on before. You're a nice guy. You've cooperated so far. And so, perhaps I'll continue to cooperate today. So I'm going to know the history of my opponent's interaction with myself, but I'm not going to know anything else. I'm not going to know how this person has behaved with other people. I'm not going to know anything, or won't even be interesting to know anything about the distribution of play within the population as well. But I know everything I need to know about my partner's history with me. Okay. And so the issue here is, what is the probability that, having met today, what is the probability that the game is going to go on long enough that I'm going to meet my partner again? If we're going to reinforce, if we're going to support reciprocal altruism, then I'm going to have to meet my partner again with a sufficiently high frequency. Okay. And you can do a little calculation, and you can see that in the game where the continuation probability of having another round where you're matched with another person, or you're matched with some randomly chosen person, if that continuation probability is P, then the probability that the game is going to go on long enough that you're going to have another round with the person that you're matched against now is a lower number. It's this number on the left in the inequality. It's P divided by n times 1 minus P plus P. And even if the continuation probability is greater than our threshold of 0.2, 1/5, for a large enough population, the probability of meeting my opponent again is going to be less than that threshold, and therefore I'm not going to be able to support altruistic behavior. And I guess it's worth pointing out that if you can't support altruistic behavior using this grim trigger punishment strategy, then you can't do it with anything. So in a large population, we see that the Trivers' basic simple reciprocity story breaks down because the density of social interaction is just too small, or too low. So now let's add some social structure to this picture. And you probably know that this graph that I've drawn here doesn't look anything like a social network, but it is a network that we can focus attention on for a moment. So in this network that I've drawn, we have every vertex represents, every little black dot here represents a person, and the lines between people indicate the individuals who are directly connected in the network. So if we look, for example, at the red dot, the red person, this is the Marxist on the left. Actually, I guess that would be the Republican on the left. That Republican on the left is connected to the two Democrats above him and the two Democrats below him, the two blue people. And so what this means is that at every round of the game, he is going to be matched with one of these people, okay? And similarly, everybody's going to be randomly matched with someone that they're connected with. And now we can see that even though we have a large population of individuals, every individual still has a high probability of meeting one of a very small set of people, one of his neighbors. There are only 4 neighbors in this picture. And so no matter how large we make the population, the probability that I'm going to meet the opponent I'm playing with now a second time is only going to be P divided by 4 minus 3P. So independent of the size of the population here, as long as the continuation probability of the game is greater than 1/2, we'll be able to use this Grimm trigger idea to support cooperation. But of course, this has a limit too. Let's add one more link across the graph. It doesn't matter actually where I put it. But now this single individual, or actually this individual, the red individual, and his partner on the other side on the right, are now interacting with 5 people rather than 4 people. And so they're going to require a higher continuation probability in order to agree to the Grimm trigger. And if the continuation probability falls in between 1/2 and this higher threshold, which is 0.56, everybody but the 2 individuals connected by the long link are above this 1/2 threshold, but nonetheless, the whole thing is going to break down because these 2 people are not going to want to adhere to the Grimm trigger, so they're going to defect. And if they defect, then the individuals that they're connected to, this lowers the probability that they're going to meet another cooperator, and so they're going to want, that will put them below their threshold, and they're going to want to defect as well, and so the whole thing unwinds. And the general conclusion of this is that we need to worry about how many people each individual is connected to. That number is called the degree of an individual, and the maximum degree of individuals in the population here is going to be critical for determining whether or not we can support cooperation. Similarly, what we could have done is said that you meet the red person meets the blue people with high probability and then meets other people at random with low probability. And we could have worked out a similar kind of continuation threshold that would have made this work. And again, degree of connectivity is going to be very important. This is a situation where a bit of heterogeneity actually can be costly for supporting cooperation. So I think now what I want to do is move on to a different situation, and I want to talk about the diffusion of social behavior. So I want to imagine that. So I want to consider the coordination game that we have here. And this coordination game has 3 Nash equilibria, 3 stable equilibria, or one is only semi-stable, I'll say, that we could imagine that everybody's going to agree on A, and if everybody does that, that is stable behavior. If everybody agrees on B, they're only going to get 2 rather than 3, but that's stable behavior. And then finally, it turns out that there is a Nash equilibrium in the middle, where if 2/5 of the population chooses A and 3/5 of the population choose B, then in terms of averages, and I should say, by the way, once again, I'm thinking about having a large population of people and randomly matching them with opponents. And if the distribution is 2/5, 3/5, then every individual is indifferent between whether they get A or B because the expected return is the same. And so that's the kind of the undergraduate story of this game. So now what I want to do is I want to imagine that these people are playing this game, but they're situated inside of some kind of social network. Okay, so let's look at our red player here, and he is connected by in the social network to 7 other individuals. These are the black vertices. And I should say here that social relations are symmetric in that if this fellow right here influences the red player, then the red player also influences this fellow. But there's no reason why we couldn't do this with influence going one way or going each way, but with different degrees. we could do the same kind of thing that I'm about to do now. And the answers change, but the theme of the analysis is the same. So in this social situation here, 4/7 of red's neighbors are A players and 3/7 are B players. So the expected return to playing A, assuming that you're going to be randomly matched with one of your neighbors, is 12/7. And the expected return to playing B, where the payoff is 2, if you meet, remember, if you play B, you get 2 if you meet a B player, 0 otherwise, the expected return is 6/7. So in that situation, it clearly would be in your interest to choose A. So this raises the question, what is the threshold of fraction of my neighbors playing A that I would need to have to induce me to choose A? And we can work that out. And the answer turns out to be that the threshold fraction is 2/5. So if 2/5 or more of my neighbors are A players, then I am at least as well off choosing A as choosing B. If less than 2/5 of my neighbors are A players, then I'm better off choosing B than choosing A. All right, so is this clear? Okay. Okay. So now what I want to ask is, let's admit we have this large social network, and we're going to I want to ask the question: if we have an A player, and everybody else is playing B, can that A kind of spread through the population? So here's the story that I want to imagine. I want to imagine that at different moments of time, we choose an individual and ask that individual, this individual has an opportunity to update her choice. So maybe she's playing B now, but she has an opportunity to switch to A. And we're going to choose these people one at a time. And we don't have to do it that way. We could have done it synchronously with everybody choosing all at once. But I'm going to think about it one at a time because it's a bit easier to see. And then we're going to see what happens. So what could happen, here's an instance. We're going to start with we have one red player, and here's a piece of our social network, and everybody else, I'm sorry, we have one red, the red dot is playing A and everybody else is playing B. And suppose now that oops, wrong way, that the blue player now has an opportunity to choose. And that person will see that 50%, actually, I shouldn't have drawn this with little tails. So take away the little tails. This is a 6-person network, okay? The only people in this network are this one, this one, this one, and those two. I meant to remove these little things suggesting that there are more people, but I forgot to do that. But in any event, so in the 6-person network, the blue person looks and says, well, I have 2 neighbors. One of them is playing A, one of them is playing B. 50% of my neighbors are playing A, so it's worthwhile for me to play A, and I switch to A. So let's make that happen. There we are. And now, maybe people are chosen and they don't flip, and then we get to now our blue person has an opportunity to switch, and now 2/3 of his neighbors are playing A, and so again it's in this person's interest to switch to A, and he does that, and so now we have 3 A players, and so the A population has grown. Now, after a few moments of time, now the player that I've just selected, the blue player has an opportunity to switch. But the blue player now has 2 neighbors that are playing B and only 1 neighbor playing A. And so this person isn't going to switch. And if that person isn't going to switch, then the people behind him or to the right of him aren't going to switch. And so here's where the diffusion process ends. Okay. A different path that could have happened was that the A person could have been the first person, the initial A, the one in the lower left could have been the first person chosen. And had that happened, he would have been below the threshold for keeping A. He would have switched to B, and so A would have died out. So if we start from a seed group with some A players and some B players, what are the possibilities? Well, one possibility is that the seed group could disappear. A second possibility is that the seed group could grow, as it did in this example, until it reaches some stable cluster. Or a third possibility is that the group could initiate a cascade, which flips the entire system from B to A. And we'd like to know something about when that can happen. And this is, and we can actually compute this and figure out a criteria for getting a criterion for getting a cascade. So I'm going to define a cluster of density Q. That's going to be a term of art for a minute. And this is a set of individuals or a set of vertices in this network such that each node in the set, each vertex in the set has at least fraction Q of its neighbors in the set. So if we look at the three red dots here, the density of this cluster of three red dots is 2/3. Again, the little tails are gone. Because each element in any set, each element in this set has at least 2/3 of its neighbors in the set. So the guy who I put my cursor on is the critical person, and he has exactly 2/3 of his neighbors in the set and 1/3 out of the set. These two other individuals, each one of them has, of course, all of their neighbors in the set. So this is a cluster of 2/3. This is a cluster of 2/3. And here's something that's not hard to prove, but I won't do it. Is if we have an initial, a set of initial adopters of A. Let's suppose we have a set of initial adopters of A that has a threshold of P. And they will seed a cascade. They will cause a cascade of A all through the system if and only if the set of other nodes does not contain a cluster of density 1 minus P. And I have to say, I didn't say it on the slide, but I forgot to say that this P has to be big enough that they will want to keep doing A themselves, even if it were only themselves. So P has to be at least as big as 0.4. But if they're, for example, a cluster of density 1/2, or suppose they're a cluster of at density 0.45. No, 1/2 is fine. If they're a cluster of density 1/2, as long as the remaining set of individuals doesn't contain a cluster that has density of 1/2, if it's a little bit more sparsely connected than they are, then the cluster will seed the entire population and we'll have a cascade. So here we have a cascade requirement. We can also derive a requirement for when there won't be a cascade, but there will be a stable set of A players. And of course, we can also, if we don't have either one of those, then we're going to have a cascade of B. And so those kind of determine, we can, in terms of this cluster density property, we can determine what what the outcome of the game is. And this is regardless of what the network actually looks like. This is, I like this fact because this thing is a very coarse description of the social network. The network could be, arbitrarily complicated in terms of which edge goes where and who's talking to whom, but it doesn't matter. All we need to know is this simple cluster fact. Now, if we were to, let's now look at the following game where in the cost of failure to coordinate, if you try and coordinate on B, you get 2 if you succeed. And if you fail to coordinate on B because somebody plays A, then if you played B and someone else played A, then you're going to get 0. So this is the game on the right. And so you only lose, you just get 0 rather than 2. But if you try to coordinate on A, you play A, hoping that your opponent is going to play A, and your opponent doesn't, your opponent plays B, then in this game, the modified game on the right, you're going to get -2 rather than 3. And this changes the coordination threshold to 4/7, a number greater than 1/2. And now, even though, so what's going on here, of course, is that the risk of coordination failure kind of offsets the benefits of the higher coordination amount that you can get by playing A. And consequently, in this game, a cascade can't take off. We can show, in fact, in an infinite connected graph, let's imagine we have a very, very large population. If the threshold that gets people to adopt is greater than 1/2, and if the set of initial adoptees is finite, then the limit fraction of people who are going to play A in the entire population is going to be 0. It can't take off. And we can devise similar bounds for large finite graphs. If it takes too much to get this going, in particular, if the threshold for adopting A over B is greater than 1/2, then there's, in no social network will you get A to take off and diffuse through the population. I'm now gone for 45 minutes, and if I have another 5 minutes, I think I can talk about the last topic that I wanted to mention.
You get 5 minutes.
5 minutes. Okay. And then I'm going to steal an additional minute for a summary slide. So now what I want to do is I want to examine a game that is due to Werner Guth and Menachem Yari. This is an elaboration of the ultimatum game that I mentioned at the outset. And the story of this game is the following. Again, we have 2 units of resource to deploy. Okay. Doobie, do you recognize this game?
I've seen it, yes.
Yeah. So there's 2 units of resources to deploy, and individuals can either exploit the situation. The first individual can either exploit the situation or act fairly. If the first individual and then the second individual simultaneously, without knowing what the first individual is doing, can also choose whether to exploit or act fairly. Okay. Now, after that, after they've made their initial choices, if they've both exploited the situation, then they're both going to get 0. If they both acted fairly, they're going to split the resource 50-50, each get 1. And if one has acted fairly while the other person exploited the situation, then the one who acted fairly has the opportunity to either yield or to retaliate. Okay. And if you yield, if you just say, okay, that's what happens, then you are going to get 0, or the player who yields gets 0 and the exploiter gets 2. And on the other hand, if the player who is fair decides to retaliate, then the exploiter will get 0, and the person, the cooperator, I'm sorry, what am I, wrong part of the talk here? And the person who acted fairly will get some utility C, which is the utility that you get from reacting. And this number C could be either positive or negative. And I'm going to imagine a population of people being matched up to play this. And some people are going to have positive Cs and other people are going to have negative Cs. So if you're in a situation where you've been treated unfairly, it might be painful for you to retaliate. And so even though you have just been screwed, you're going to say, all right, that's the way it is. And on the other hand, you might be the kind of person who is says, I'm going to get you for that. Okay. And for you, C is positive, and in that case, you're going to retaliate. Okay. So that's the story of this game. I'm going to tell the story very quickly. So what I'm interested in here is not in evolution of play of the game. In this game, when people are matched, each person knows the C value of the other person. There's only 2 possible values. One is positive, one is negative. And the 2 C values completely determine what's going to happen in the game. If 2 positive people meet with each other, okay, people who like to retaliate meet with each other, they're going to know that. And this game will have a unique equilibrium outcome, which is they split the resource. If they did I do this the wrong way around? I did this the wrong way around, I think. No, I don't think I did this the wrong way around. Well, I did do it a little bit wrong. Okay, if this box is wrong, if two non-retaliators, oh no, I didn't. This is right. If two people who like to retaliate meet each other, they're going to split the resource and they're going to get one because it doesn't pay to fight. If two people who don't like to retaliate meet each other, each knows that they're playing with someone who doesn't like to retaliate, and so they're going to both exploit the situation, and they're going to end up with 0, and that's the unique equilibrium outcome in that game. And if someone who likes to retaliate meets someone who doesn't like to retaliate, then the person who likes to retaliate can exploit the person who doesn't like to fight, and get all the resources for himself. So the behaviors are completely determined, but what I want to talk about is the evolution of preferences. So we might imagine in this game some kind of dynamic. It could be reproduction in a biological setting. It could be imitation in a social setting. It could be that people are learning, or their preferences are formed by somehow conforming with what other people are doing. There's a variety of social stories that one can tell. Whereas evolutionary game theory largely talks about the evolution of play within a game, what we can do here is talk about the evolution of the game itself. We might say, ask the following question: if there is some kind of dynamic that says, for example, if retaliators do better than non-retaliators, then the share of retaliators will grow in the population in the next round. If non-retaliators do better than retaliators, we'll get the reverse result, and the non-retaliators will grow in the next round. What's going to happen in the game over time? What kind of preferences will come to dominate? So the game will actually be changing in the population as people's as the distribution of preferences within the population changes. And you can see in this game, I didn't bother to kind of lay this out in any detail because I knew I'd be out of time, that no matter what kind of evolutionary story that we want to tell, if you're a little bit familiar with evolutionary game theory, you'll know about things like evolutionarily stable strategies or replicator dynamics. And those are actually concepts that apply to play of the game, but we can, in this setting, also apply them to preferences and say, what kind of preferences are going to be evolutionarily stable? What kind of preferences are going to be steady states in the replicator dynamic, or in any other kind of dynamic that actually respects payoffs? And what's going to happen here is that the share in this particular game is that the share of people who like to fight is going to grow to 1. So what's going to happen here is that preferences will evolve, not preferences themselves, but the distribution of preferences in the population will evolve over time. And in the long run, everybody's going to be playing the game with people who like to retaliate. They themselves like to retaliate. And out of that, the fair outcome will emerge. So I actually really like this kind of story because I think that this is really where the action is, in some sense, that preferences are not given ex ante. They're not encoded within us, from the moment of our conception or something like that. Instead, preferences are partly socially constructed, and this is a model of how the social construction of preferences might work. And instead of just trying to understand how people, what kind of social situations actually support altruistic among self-interested people, we might ask how self-interested play might evolve to self-interested preferences might evolve to some other kinds of not quite self-interested preferences. There's a stream of research that I wanted to mention. I really like these papers a lot. And it would be worth having a talk on this, by the way. Jürgen Weibel Ingela Auger have a bunch of papers where they look at asymmetric matching in some kind of game that has to do with resource distribution. They discovered that asymmetries in the matching process can induce the evolution of pro-social preferences, where you at least favor people who are within your group. They talk about this as the evolution of Kantian morality. I think that's a misunderstanding of what Kant is, but no matter how you understand the result, it turns out that this idea actually has some legs and can say something in games that are much more interesting than the games that we've talked about here.
Can you go back, please? What are the preferences that you were talking about in?
All right, so if you look at the payoffs in the game,
Yes.
right, it's the number C.
Okay, it's the number C. Okay. Okay.
Yeah, is it the negative number or the positive number?
Oh yes. Okay, I get.
All right. So this is the simplest possible story.
Yeah.
Okay.
Okay.
Other questions? Okay. So here's a bunch of takeaways that obviously, and I think we all knew this coming into the talk, that pro-social behavior can be rational for self-interested actors, but social structure can matter, and it can either help or hinder the support of pro-social behavior. In the same kind of game where pro-social behavior can emerge, antisocial behavior can also be rational, and which actually takes off may depend on very fine-grained details of the system. And you might think about that in terms of that number A in the coordination game. If A is 0, then you get the diffusion of pro-social behavior. If A is large, you get the diffusion of the B equilibrium rather than the A equilibrium. And obviously there's a threshold, and you move A a little bit across the threshold and the whole system switches from diffusing to A to diffusing to B. The other thing is, and I didn't talk about this at all because there wasn't time, but you might look for multiplier effects in these systems. And you can actually see that in the coordination game, because the question that we asked there was, if we had a small group of people doing one thing, does that lift to the if we could somehow come in and influence a small group of people to change their behavior, does that then cause diffusion throughout the system? Right. And so we might look for, if we want to make some kind of behavior in the system go viral, who in the network are the critical people to attack? And there is a large and recent literature on exactly this question in the computer science community. And finally, the last point is that it's perhaps more interesting to look for evolution of the game rather than the evolution of behavior within the game. And with that, I'll stop.
Okay, let's start with a discussion. I'll ask some clarification question. So how preferences are changing? The C's, what is it? It's by what makes them change?
Okay, so think about every story you've ever read about the replicator dynamic, right? And so in a biological system, right? The numbers that we would have represent fitness, right? Which is probability of having offspring. Okay, yes. So then we would be telling a generational story. In a social setting, we might imagine, so I think actually the social stories for this are a little bit weaker. But if you think, for example, that there is pressure to conform, or if people are looking around and saying, wow, the person this other person over there is doing better than I am. Maybe I should try and mimic their behavior, right? This leads to a kind of imitation dynamic. And you know that there is an imitation, a version of imitation that leads to the replicator dynamic. Okay.
Yeah, but the imitation is imitation of action, not imitation of taste.
Well, but it could be imitation of tastes, right? It could be high level imitation rather than low level imitation, right? That's up to the modeler, right? If your tastes, if you imagine this, that if you really have an aversion to punishing people, right, then it's hard to mimic their action. But if you can say, wow, I really need to adjust the way that I think about these situations, that's a higher order level of change, right? But we do make these changes all the time throughout our lives. Okay, and ways in which you behaved when you were young, ways in which you behave, maybe not you do because you're a very stable person, but people do change. I think that people do adjust their views of the world. Maybe a version where this is more telling is to think about this in terms of adjustment of beliefs about what's going on within the population, right? So and beliefs are one component of preferences. So there have been a number of papers in the political science literature that have been written about the diffusion of beliefs in social movements. The one paper I'm most familiar with is that me? Is a paper by Suzanne Lohmann, who was motivated by the Leipzig demonstrations that led to the collapse of the East German Wall and the collapse of the German Democratic Republic, so she begins, her story begins with a bunch of people who go out and demonstrate every day, and then people observe that, wow, it seems, at different moments in time, people begin to observe that one can go out and demonstrate and there don't seem to be consequences, and then they go out and join the demonstration. This increases the signal effect of the demonstration going on, and then more and more people go out, and then in the end, you have thousands of people in the street, and then in the end the wall comes down. So that story that she tells depends a lot upon heterogeneity within the population, because you have a core group of radicals who just go out there and start doing things regardless of the consequences. But then over time, what happens is that people begin to learn that the consequences aren't as great as they thought. And if there is heterogeneity in the threshold of how safe does it have to be in order for this, in order to make it worthwhile for you to go out and demonstrate, then you'll get this growth over time of the group that goes out there. And this is kind of a first order story about the spread of social movements. I think it's actually really, it's not a terribly deep story. One might compare, the demonstration in Leipzig with the demonstrations in Belarus, and wonder, why is it in Leipzig that they took off, but in Belarus they didn't? And one explanation is that in Belarus they jailed all the demonstrators. Another explanation is that in Leipzig, people in the police force were also demonstrating, and so there's a lot of fine-grained stuff that makes a difference. But that's an example of number one. It's another example of a multiplier effect, and number two, and an answer to your question, that's an example where preferences are changing, and then the changes in preferences lead to the change in behavior.
Yeah, well, preferences are changing. That's trivial. I mean, but usually they're not changed by you or by that. It's changed by external forces that work on us to change our preferences.
Well, but that's what's going on in Lohmann's story, right? The external forces are what you see, right?
Yes.
Right. But it's within, so there's a question of do preferences change endogenously or do preferences change exogenously?
Exogenously, yes. By exogenous forces, yes.
Right. And I'm kind of interested in endogenous preference change, because I really don't think that we should take preferences as
Have you read Fishing for Fools?
Pardon me?
Have you read Fishing for Fools with PA?
I have not yet.
Okay, recommended. That's a book about changing your preferences.
Yes.
As a fool.
Which way do you move? That's.
Okay, good. Yeah.
So the ideas that I all the models that I presented today, I think are really very shallow models, but the reason I chose them is because I think that they are in fact, you see these models or models like them in much richer situations. These are kind of the basic ideas that underlie more complicated models that I've seen in a number of different literatures, in biology, in political science, in economics, in computer science. And so I hope what I've done is to you know, give you a taste for seeing how these kinds of ideas might play out in settings that we actually care about. You know, rather than in the classroom settings, which I've given here. And actually, I've decided I'm teaching evolutionary game theory at 1 o'clock this afternoon, and I'm going to actually use the same lecture because I'm just exhausted with Zoom in the classroom, as we probably all are. I've actually run out of material. So, because Zoom lectures go faster. So I'm going to talk about this.
Okay. Any comment from a biologist? Yes, Arnon.
Yeah, I have a lot of them. I have two questions. One, when you talk about this evolution during the game, I mean, for me, it's kind of, you talk about imitation. It was not clear to me, are you talking about imitation with feedback or without feedback? Because I can imitate and then see what happens, which means I use learning to choose my strategy, okay? Or I can just imitate and just, you know, enjoy from imitation. I mean, what kind of feedback you consider in this process?
All right, so you know, in the model that I presented here, I actually thought about it as a generational model, where one generation, you know, how do I want to say this? A generation plays the game and dies, but I'm looking at the standard ESS story, right? Or the standard replicator story, where there's a new generation, but the propensity to reproduce comes from the outcome of the game in the previous generation. So there's actually not a feedback within individuals, right? But you could imagine the model. So when people, you know, but the replicator model also is, the replicator dynamic is also a model of imitation. So I can write down an imitation where I just look around and see what, you know, whatever my selector is, I look around and see which selectors are doing better, and then I imitate them at some rate, okay? And so that is a model with feedback, and you can do that with, so social learning models, of the kind that, for example, Drew Friedenberg wrote down, that Brian Arthur and David Lane wrote down, these models actually behave exactly the same way, right? The model that I described of Suzanne Lohmann's is actually a Bayesian learning model. And because she was really not adept at thinking about Bayesian learning, if you look at the paper in World Politics, it actually has a fold-out page where you pull it out, and it's now like a twice as large page where she actually has the updating formulas, because she didn't know about martingales. It's kind of funny, but
So she invented the martingales?
did she invent them?
No, yeah. She
Sure.
rediscovered them or what? Or she didn't use them?
No. She actually just ground it out by hand and said, "Here's the result." Right? Pages and pages of algebra. Okay. So you can, you know, so you can build a model that has that demonstrates the phenomena that I described, either with feedback to the current generation of actors or without. Okay. Either way.
Mm-hmm. Yeah, I see.
Mm-hmm.
Okay.
Mm-hmm.
Yeah.
And I guess I wrote the table down the way I did so that you could see that if you like the ESS story, immediately what the answer had to be.
Okay, well, I get it.
No.
I can ask you, I can also ask another question if there's no one else. You described this preference evolution. I mean, right now, with the last example of the ultimatum game, but I assume you can use it or you know, develop it for cooperation game as well, right? I mean, for many, even for
Yeah,
super.
yeah, you can. Yes, you could.
Yeah, I just wanted. Yeah, it seems to me that actually with the cooperation game would be a simpler case, maybe because these. Yeah, but maybe it's the same. All right. No. I should read it more carefully, I guess.
Mm-hmm. So one of the, you know, the challenges I think, you know, so Hume had this idea that informal social arrangements will take us a long way. And Hobbes had the idea that it's government, and above all, having a sovereign, having a king, right? That's going to, kind of solve the social dilemmas. And I think the challenge is so my way of thinking about the evolution of institutions is that the evolution of institutions happens kind of at what I think of as the reciprocity boundary, which is what happens when the scale of a community gets sufficiently large, when the social interactions become sufficiently, when you lose enough of the repetition, for example, in the altruism stories, that you need other institutions to support reciprocal behavior. There's a paper by Joy E. Deb. This is actually her PhD thesis, I think, where she wants to ask what happens in an extremely large social networks when and very, with very small degree. Okay, so that most people are connected to very few people, but the population is very large. Can you still support cooperative behavior? And the answer is yes, but it's yes in a very non-credible way. So you might imagine that, go back again to the basic reciprocity story, and individuals. So here's the idea: everybody cooperates, and if your opponent defects, but she changes the information story in one way, everybody knows how everybody else behaved. Okay, so everybody knows the entire history of play in the population. So if you do that, right, then when one individual defects, if Doobie plays with me and he cheats on me, and then he goes to Elan to play, and Elan said, "Oh, you treated Blume badly, so now I got to punish you." Okay, and so you think, well, that might work. Okay, to support cooperation, but then you have to ask the question: but why, Elan, is it in your interest to punish Doobie for how he treated me? And the answer is that next period you might get matched with Zvi, and he's going to punish you for not having punished Doobie, okay, for having punished me, okay. And now, why is Zvi going to play that way? And you can imagine how this just takes off, right? So so it turns out that you can build these very elaborate, delicate equilibria that support cooperation, but they're really just not credible, right? I don't think we believe that people behave this way. So there comes a point at which we need to have institutions that support really anonymous kinds of things in something like a prisoner's dilemma, or it might be that prisoner's dilemmas are just not solvable. So this is a very different view, for example, than the Acemoglu and Robinson stories about the rise of institutions and what they do. And I think that this is a fruitful area for research. But that's just me.
That's it.
Well, I guess next time I'm in Ithaca, we should talk more, because
well, please come.
I'm doing some social learning, and we've done some game theoretical model about social learning, but it's I think it's really different. I mean, we are interested in learning when animals really get the feedback, and because normally when animals try to learn from each other, okay, they do social learning, but they either get food or get what they want or not. So the feedback is there if you want it or not. And then it really depends on many circumstances. Anyway, I found direction. I should just read the papers and get, it's difficult right now, but it'll be interesting too.
Have you written on social learning at all?
Yes, I mean, I'm experimentalist, but also in the past I did some reciprocity work, actually evolutionary game theory and simulation with reciprocity and indirect reciprocity, but this was a bit, this was nearly 20 years ago.
So can I ask you a question then, since you're experimental? What is the story with these bats? Are they related?
Oh, you mean the vampire bats? Was this reciprocity story? Well, I don't know enough about the bats. I read the papers like you can do, like you can. Some people suggest that there is some genetic relatedness as well. I'm not sure that I know how it really works there. This is kind of the classic example of reciprocity, and some people are a bit skeptic about it. And so I don't know what to tell you about this particular case, but in general, I think that when you look in realistic population, you have many other factors which it's all together. You have genetic relatedness, you have reciprocity, and you have also many asymmetries. And you have reputation, and I guess you know the models of indirect reciprocity or good standing, or it's become very messy. And I found that for me, the reason I'm not using so much the game theoretical model or ESS models is because I'm more interested in learning, and the more you deal with learning, these models are it's become messy to a model to handle the learning dynamics and. Animal do use learning, but it's a whole, we should catch a point of talk. It would be nice, actually.
So one model of learning, I think that is useful for thinking about, there's a question about whether it's a psychologically accurate model. I think it's probably not, but it is useful, I think, for seeing how learning itself can diffuse, is to think about the de Groot learning model. Do you know the de Groot learning model? So that everybody is trying to learn the probability that something is going to happen, and everybody reports a probability, and people live on a network, for instance, and they report their probability, and then at the next round, everybody reports again the average of the probabilities that they heard, including their own. So if I'm connected to 5 people, these 5 people tell me what they currently think the probability is. I take that information together with my own belief. I take the average of all those. That's my new belief. And now at the next round, I report that. Okay. And it turns out that actually behaves just like it behaves just like Markov processes. Okay. If you like that learning model, you can show what happens is that beliefs, except in a couple of very rare instances, beliefs always converge, and everybody at the end ends up believing the same thing. And you can talk about how fast do they learn. And this really depends upon the properties, the topological properties of the network, actually the second largest magnitude eigenvector of the adjacency matrix. And you can do this where different people have different influences on you. So I might weight one neighbor a lot and other people's opinions less so. And that's a very powerful model and a pretty simple one to operate.
Yeah, but this assumes also that if you all converge to the same idea and we like the same things, that what we're doing is like for example, in nature, if you assume that doing the right thing is a resource, then if everybody is doing the same, actually the resource will be sooner. So actually it's also a game problem, because sometimes maybe it's not, there might be advantage to believe in the rare strategy.
Right.
Okay, so, and then you might not get convergence, like a uniformity.
Right. So if everybody has the goal of learning, and everybody and even if you have diverse beliefs, if you send me an email, I'll send you back a paper by Matt Jeff,
well, I can send you
that gives conditions under which learning takes place. I think it's actually a problem that I set for my graduate students is to think about fake news. So suppose that you have in your social network somebody who's pumping out, what they believe or what they want to say, and not paying attention to anybody else, and doing this on purpose. Okay. So even one person doing this in the network keeps it from really settling down. Okay. It shows, in fact, how non-robust learning can be, because a fake news pump can destroy learning, even if if the number of fake news providers is a pretty small part of the population.
So in this model,
much less when it's Fox News, right? So
in this model, there is no the beliefs are not anchored in any facts. Okay, so it's not really that you.
All right, so you don't necessarily right. This is correct, and since if beliefs are not anchored in fact, then beliefs will not necessarily converge to the truth. So
Well,
here
that's
is
the
a
thing. I
model,
mean,
though.
there's no truth. Not that it's not converged to truth.
Well, then there is no
truth defined
truth.
in the law.
Right. We just learned to conform.
Yes.
But on the other hand, you might say that there's a fact out there, and everybody makes and everybody makes an assessment. Okay. Gets a signal, and then this gives you a belief about whether the facts, this gives you a belief, and then you start pumping those beliefs into the
Yes,
system.
but once you average the beliefs that you heard, then it drives it away from anything which is realistic. I mean, it's not that
So
not that you
Matt's theorem,
not updating of beliefs.
right? Matt's theorem is exactly that. If everybody draws, gets a signal, and then a probability signal, and then pumps that signal into the system, and then they all start averaging. Okay, then you obviously are going to converge to something. Okay, and then the theorem is that if the population is very, very large in this network, keep the degree constant, but make the population very large. So now what's happening is that the aggregate population signal is getting very accurate, even though each individual is getting a very inaccurate signal. And what will happen then is that there's a law of large numbers at work. You essentially converge to the truth.
Mm-hmm. I see.
Okay. So that's the theorem. But I don't think that converging to the truth is really the interesting part of this.
No. Okay.
Mhm.
Mm-hmm.
Yeah, I think it's the coordination of beliefs and the loss of heterogeneity that I think is to me is the most striking part of that.
Mm-hmm. Okay. Okay. Thank you very much, Larry.
Oh, this is a lot of fun. Thanks for coming. I hope you got something out of this, and I'll be looking forward to an email.
Yes, I will be in touch. Yeah,
Haven't you met before?
long time ago.
Because